In this video, we're going to talk about buffer overflow. So one way to look at buffer overflow is in terms of these individual bit buckets. So let's just assume that we have a bunch of these bit buckets in our main memory of the computer, and one of these bit buckets is called a buffer, which stores input from a user. So when everything goes the way it's supposed to go, I don't think we have any issues. But sometimes, either intentionally or unintentionally, a user can provide too much information in this bit bucket called buffer, and that information can overflow into other types of buckets or other buckets containing other critical information for running an application. So for example, when the buffer bit bucket overflows into this bucket containing local variables and wiping out or contaminating the information inside the local variables bit bucket, then the program is not able to run properly, or maybe the important information stored in the local variables could be manipulated or changed, which is not a good thing for security. Another thing that can happen is the bits in the buffer bit bucket can overflow into a bucket containing a return address of a program thread of execution. And what could happen is, instead of going to the next line of code that's supposed to be executed, you can change the flow of the execution of your program and go to a particular line of code you want to execute as a malicious user. In this case, it could be a piece of malicious code you want to run as an attacker, which could be really dangerous. But in reality, we don't really have these buckets in your main memory. So this is actually what you have in your physical memory. So as you can see, the memory is divided into various sections, which include heap, stack, and also areas containing global data and program instructions. So this is what it is in reality. And as you can see, the areas in your memory designated as stack, it's actually growing in the opposite direction of the direction the heap is growing. And we'll talk about what we mean by the stack and heap in the next slide. So stack is defined as a scratch space for a thread of execution. And what this means is that when you are running a program, sometimes you have to go out of your normal flow of execution because you have these things called functions. So when you hit this function, you have to go to an entirely different area of your memory and then execute your code within that particular function. So when you do that, you have to have a special place to store, for example, arguments for the function and also the local variables within the function. So whether that's a string or whether that's a number, you have to have a place to store those, and that's what really the stack in the memory is doing. So when you add things to the stack, it's done in the fashion called FILO, which stands for first in and last out. So that's why, for example, as you can see in the picture here, whenever you add something, the stack section of the memory, it gets bigger, and the way it's growing, it's actually going downward. And let's say you added some parameters after you added local variables, that goes on top of, for example, the local variables, and whatever you need to add more, it will go on top of, for example, the parameters. So as you're done with your execution of the function, these areas of your memory designated as stack will get freed, and the way it's being freed, the fashion, is really first in and last out, because, for example, parameters will be removed to free the memory, and then the local variables and so on, although the way things were placed into the stack was in the opposite direction. So, for example, local variables were put into the stack first, but then it is going to be removed last. The parameters were put in the last, but then it will be removed, but they will be removed first, and so on. But in reality, when you are using these functions, I think in general these things constituting a particular frame of stack, they move as a unit. So the entire stack frame, containing all the information related to a particular function, they will be, for example, placed into the memory, and then they will be released from the memory together. So the example I used is a little inaccurate, and you have to understand, for example, if you have another function call, a particular area of your memory gets allocated to accommodate that particular function call, which will be added on top of the existing stack frame, and so on. So in the picture you see some terms like frame pointer and stack pointer, and I'm going to explain what they are. Frame pointer means the address of the beginning of a stack frame, and it just stays there all the time just to provide some sort of a reference point for the stack pointer, and it's really pointing to the physical address of the beginning of that particular stack frame, a unit of stack area holding information for a function. And stack pointer constantly moves to point to the end of or the top of your stack frame, as you can see in the picture, and the stack grows downwards, as you can see also in the picture. Okay, now let's talk about heap. And heap is memory set aside for dynamic allocation. So for example, when you are instantiating a new object in your C++ code by issuing a command such as new class X, as you can see in this slide, that's the space of the memory used by this particular call. So then what are the consequences of buffer overflow? The consequences could include crashing the application, or the application crashing because the buffer overflowing is overriding an important section of your memory, whether it is a variable containing important values or a section of your memory containing some important memory addresses such as return address. So if that information is wiped out, your program doesn't know where to go next. Another, a little more advanced way of manipulating your memory by overflowing your buffer is this execution of malicious code, and this is what we're going to be doing in our lab. And what this does is, by overriding a very special area of your memory containing the return address of your program, you can actually direct the program, the thread of your program, to a malicious piece of code you want to execute. Therefore, by executing malicious code instead of going back to the normal flow of your own program, which is really bad. So finally, there are ways to prevent buffer overflows from happening, and we call them buffer overflow countermeasures. And these countermeasures can be, for example, something related to secure coding practices. So when you're writing your source code, if you use safer function calls, that can definitely help reduce these buffer overflow problems. And also, if you enable compiler warning messages related to the use of dangerous functions or the possibility of buffer overflow found in your code, that can also help you reduce the number of buffer overflow vulnerabilities in your own source code. Another, a little more difficult way of doing it is using this mechanism called stack execution invalidation, where a malicious person tries to execute his or her own code through buffer overflow attacks. Your system is smart enough to detect that and then prevents that malicious code from being executed.